I once again welcome you to MSP lecture series on main group chemistry. Let me begin my talk today on group 2 elements. Group 2 elements are known as alkaline earth elements. This group consists of beryllium, magnesium, calcium, strontium, barium and radium, and the electronic configuration of alkaline earth elements is Ns2, that is valence electrons. That means, we have 2 electrons in the valence shell. As a result, the group oxidation state is +2, and as expected, being the first element, beryllium differs from other elements owing to its smaller size. In fact, beryllium resembles more of aluminum than magnesium and calcium, and that is about diagonal relationship between beryllium and aluminum. I will discuss those aspects later. And atomic and ionic radii are smaller than those of group 1 elements. Of course, here one electron is added to the same shell and nuclear charge is also increased. As a result, one can expect the atomic and ionic radii of alkaline earth metals smaller than the corresponding group 1 elements. The alkaline earth metals are named after their oxides, the alkaline earths, whose names were beryllia, magnesia, lime, strontia and baryta respectively for beryllium, magnesium, calcium, strontium and barium. These oxides are basic when combined with water. That means, these oxides, when they are reacted with water, they give hydroxides, the basic solution. As a result, they are called as basic oxides. Earth in these elements is referred to earlier essentially for non-metallic substances. Earlier the term earth was added since they were insoluble in water and resistant to heating, and of course, these properties are shared by these oxides and hence they are called alkaline earth metals, and they readily form M2 plus ions since the group oxidation state is +2, and as expected M2 plus ions are smaller than M. Atomic and ionic radii increases down the group as the size increases. This is the periodic trend we are familiar with, and ionization enthalpy decreases down the group. First ionization enthalpies are higher than those of the corresponding group 1 elements. This is again following the same expected periodic trends, and second ionization enthalpies are higher than the first ionization enthalpies for all alkaline earth metals. Now, you can see here the ionization energy of group 2 elements are shown here. For example, you can see first ionization energy is much higher, and the second ionization energy is shown here, and overall the ionization energy of all alkaline earth metals are shown in this plot. And you can see here the first ionization energy or ionization enthalpy of all alkaline earth metals are much higher than those of alkali metals or group 1 elements. I already mentioned why. So, then hydration enthalpy. So, this hydration enthalpy decreases down the group due to the increase in the ionic size. As the ionic size increases down the group, charge to size ratio also decreases. As a result, what happens? Hydration enthalpy, that depends heavily on the charge to size ratio, decreases due to the increase in the ionic size and decrease in the charge to size ratio. As a result, one can expect the trend in this fashion. for group. So, due to the larger size, group 2 elements are more extensively hydrated compared to group 1 elements. For example, if you see magnesium chloride is 6H2O, that means it has 6 water molecules. Similarly, calcium chloride can take up to 6 water molecules. If we compare these things with so a sodium chloride or potassium chloride, they do not form hydrides. Okay. So, that is the difference between group 1 and group 2 elements, and similar to group 1 metals, group 2 metals are also silvery white in color, soft but harder than group 1 elements. The hardness, relatively more hardness compared to group 1 elements, comes because of the availability of 2 electrons for metal-metal bonding. A strong electropositive property is shown by group 2 elements, and this trend increases down the group. All these properties are displayed here, whatever I said so far. So, let us look into the properties of group 2 elements, and the trends whatever I said can be clearly seen here in the metallic radius. Metallic radius, as expected, is increasing from beryllium to radium, and ionic radius also should increase, and it is increasing with beryllium showing 27 picometer, whereas radium showing 170 picometer, and first ionization energy is decreasing as the valence electrons are moving farther from the nucleus. Ionization of those electrons would be rather easy, that you can see here. That is also reflected in the reduction potential here. Reduction potential you can see here, the trend, and the density is given, and melting point also decreases down the group, and enthalpy also decreases, and so all these properties are according to the periodic trends one should expect by looking into the trends seen along rows and also down the group. Let me tell you a little bit about alkaline earth metals and who discovered. And as I mentioned, all alkaline earth metals are silvery white in color. So, you can see here beryllium I have shown here, beryllium, magnesium turnings I have shown, calcium, strontium, little gold color is there, freshly sublimed one, and barium and radium is radioactive. Beryllium was discovered by Louis Nicholas Vauquelin in 1798, and magnesium was discovered by Joseph Bloch in 1755, and Humphrey Davy, in fact, he has contributed significantly to the understanding and growth of chemistry, especially alkaline earth metals and alkali metals and alkaline earth metals. In fact, he is responsible for discovering and isolating in the pure form many elements that I will be discussing in the next slide, and he is responsible for discovering calcium, barium and strontium. Strontium was collectively together discovered by Crawford and Cruikshank in 1790, and later it was isolated in its pure form by Humphrey Davy, and Marie Curie and Pierre Curie, they discovered radium in 1898. And of course, as I mentioned, Humphrey Davy's contribution is remarkable. He just lived for 51 years, and he is known for the electrolysis and also giving the method of isolation of and discovery of elements such as aluminum, sodium, potassium, calcium, magnesium, barium, boron, and also he is well known for his safety lamp, also known as Davy lamp, for people who work in the mines. Okay, so let us look into the occurrence of alkaline earth elements. Beryllium occurs naturally as the mineral beryl, important ore of beryllium or important source of beryllium, with composition Be3Al2SiO3 6 times, and magnesium is the 8th most abundant element in the earth's crust and the 3rd most abundant element dissolved in seawater. It is commercially extracted from seawater, and the mineral dolomite. Dolomite is nothing but a combination of calcium carbonate and magnesium carbonate in 1:1 ratio, and calcium is the 5th most abundant element in the earth's crust, but only the 7th most common in seawater. due to the low solubility of calcium carbonate. And of course, calcium is a major component of biominerals such as shells and coral, and calcium, strontium and barium all are extracted by electrolysis of their corresponding molten chlorides. Radium can be extracted from uranium bearing mineral such as pitchblende. All its isotopes are radioactive, and beryllium is extracted by heating beryl with sodium hexafluorosilicate, that is Na2SiF6, and magnesium is the only group 2 element extracted on an industrial scale. Magnesium, calcium, strontium and barium can be extracted from their respective molten chlorides, very similar to Downs process employed in the extraction and isolation of sodium from sodium chloride. Calcium is extracted by electrolysis of the molten chloride, which is itself obtained as a byproduct of Solvay process for the production of sodium carbonate, and strontium is extracted by electrolysis of molten strontium chloride or by reduction of strontium oxide using aluminum, very similar to thermit process, and barium is extracted by electrolysis of the molten chloride or by reduction of barium oxide with aluminum. That means, essentially we have two methods at our disposal to extract strontium, either from molten halides or from the corresponding oxides. So, when it comes to radium, all isotopes of radium are radioactive. They undergo alpha, beta and gamma decay with half lives that vary anywhere between 42 minutes to 1599 years for some of their radioactive isotopes, and radium was discovered by Pierre Curie and Marie Curie in 1898 after painstaking extraction from the uranium ore pitchblende. And in fact, pitchblende is a complex mineral containing many elements. It is besides uranium, it is a source of many trace elements and also some of the radioactive isotopes of some of the heavier elements, and it contains approximately 1 gram of radium in 10 tons of ore, and in fact Curie's together took nearly 3 years to isolate 0.1 gram of radium chloride from pitchblende. Okay. So, let me give the extraction method of beryllium starting from beryl. So, as I said, beryl is nothing but Be3 Al2 SiO3 6 times. Okay. So, first it has to be treated with hexafluorosilicate, sodium hexafluorosilicate. Okay. So, it gives Na2BeF4. So, it acts as a fluorinating agent, and then this is treated with sodium hydroxide, leads to the formation of sodium fluoride, and BeOH will be separated, beryllium hydroxide, and on treatment of beryllium hydroxide with this salt, gives beryllium tetrafluoride, okay. This one on heating gives beryllium fluoride. So, this beryllium fluoride on reduction with magnesium gives pure beryllium through the formation of magnesium fluoride. So, this is the method used for the extraction of beryllium starting from beryl. So, let me give the extraction method used in the case of magnesium. As I said, in case of magnesium, okay, one can use molten magnesium chloride. Molten magnesium chloride, and that means preparation of magnesium chloride involves the treatment of magnesium hydroxide with HCl essentially a neutralization process giving the salt and water. Okay. So, in molten electrolysis at cathode, so at anode so reduction of chloride takes place. Okay. And this is for magnesium. The similar method in case of strontium and barium as well. In case if you have oxide, one can use aluminum. Of course, here to initiate the formation of aluminum oxide that is highly exothermic, first the reaction needs triggering. So, this method one can conveniently use in case of barium as well. So, other method of molten will be similar to this reaction. Now, let us look into the flame test. We are familiar with flame test in case of alkali metals. Similarly, in case of alkaline earth metals, calcium imparts brick red color, whereas strontium imparts crimson red, and barium imparts characteristic apple green color to the flame. And with this, let me begin the discussion about the chemical reactivity of group 2 elements. Of course, when we are looking into the reactivity, we follow this sequence. Let us look into first reaction with hydrogen to form hydrides, and then with oxygen to form oxides, and maybe with other chalcogens to form the corresponding chalcogenides, and the interaction with water, and then halogens and nitrogen and other reagents, and then its reducing nature and also behavior of alkaline earth metals in liquid ammonia. Okay. So, this is the flame test you can see here. So, calcium, strontium and barium all have shown, and in fact, because of these vibrant colors they are also used in fireworks. So, before I proceed to consider the reactivity of alkaline earth metals, let us look into the difference in the properties of beryllium from the rest of the elements, and that means the anomalous properties of beryllium should be looked into, and let me discuss those properties. Generally, beryllium forms covalent compounds such as beryllium halides, BeCl2, BeBr2, beryllium iodide, and also with hydrogen it forms covalent hydride BeH2, and they have a tendency to form complexes because of larger hydration enthalpy with the formation of molecular compounds such as beryllium acetate. Hydrolysis of beryllium salts in aqueous solution leads to the formation of species such as BeH2O thrice OH plus acidic solutions, and hydrated beryllium salts tend to decompose by hydrolysis reactions where beryllium oxo and hydroxo salts are formed rather than by the simple loss of water. So, that is the speciality of beryllium, and the oxide and other chalcogenides of beryllium adopt structures with a more directional coordination structures. That means, essentially they form some coordination compounds very similar to transmetal coordination compounds, having preferably 4 coordination. Okay. So, beryllium forms many stable organometallic compounds as well, including dimethyl bore beryllium, diethyl beryllium and dibutyl tertiabutyl beryllium, and also it forms berylocene similar to ferrocene, that means bis cyclopentadienyl beryllium compound. And of course, since I am devoting a few lectures for the organometallic chemistry of main group elements. That time I will be elaborating more about the synthesis and stability and structural aspects. And both beryllium and aluminum form covalent hydrides and halides. The analogous compounds of other group 2 elements are essentially ionic in nature. The oxides of beryllium and aluminum are amphoteric, whereas the oxides of rest of the group elements are again basic. This is also the trend very similar to what we saw in case of lithium. In the presence of excess of hydroxide ions, beryllium and aluminum form tetrahydroxy species like BeOH 4 times, 2 minus. Of course, aluminum forms similar soluble hydroxide. No equivalent chemistry is observed for, whereas magnesium does not show any of these properties. And both elements form structures based on linked tetrahedra. So, beryllium forms structures built from minus and BeX4 X minus tetrahedra, and aluminum also forms numerous aluminates and aluminosilicates containing AlO4 N minus units. So, this shows the similarities in the reactions and properties of beryllium with aluminum, and both elements form carbides that contain C4 minus ion. Of course, in carbides these ions will be there, and which on hydrolysis or reaction with water produce methane. The other group 2 carbides contain essentially C2 2 minus ion and produce ethylene. This essentially gives ethylene or acetylene. Of course, those things I will discuss later, okay, when the corresponding carbides are treated with water. And alkyl compounds of beryllium and aluminum are electron deficient compounds that contain bridges. That means essentially this is nothing but 3 centered 2 electron bonds. Okay. So, this is quite common in case of alkyl beryllium and aluminum compounds, and they undergo association to form one dimensional chain. So, I will be elaborating later about the more details about this one. So, let us now continue with the chemical reactivity of group 2 elements. Smaller size compared to alkali metals. We should remember alkaline earth metals have smaller size compared to alkali metals, and they are strongly hydrated, and they have high lattice energy compared to group 1 elements. And in fact, beryllium has a different chemistry compared to its heavier congeners. Free beryllium 2 plus ion does not exist. All its compounds are covalent or contain solvented ions such as, yes, that means it is very difficult to isolate free beryllium 2 plus ion. Many of the salts are less soluble in water. Okay. K2SO4 is soluble. Okay. Many of the group 2 salts are less soluble in water. For example, K2SO4 or Na2SO4, if you take, they are soluble in water, whereas CaSO4 or strontium SO4 are insoluble. In fact, the trend increases down the group. In fact, most of the barium salts are insoluble, and beryllium is a rare element, and its ore is important ore or source is beryl Be3Al2Si6O18. Of course, let me stop here. In my next lecture, I will be continuing the chemistry of main group 2 elements and begin my lecture with group 2 hydrides. So, have a pleasant inorganic chemistry reading. Until then, thank you.